Hi dear students, welcome to online classes. I am Virpoksh VP. In last class we were discussing about ionization energy. What is ionization energy? The minimum amount of energy required to remove an electron from outermost shell of an isolated gaseous atom is called ionization energy. In today's class we are going to discuss about trends of ionization energy in periodic table. In a period, ionization energy increases from left to right in the periodic table. Why ionization increases? Because from left to right, atomic radius decreases and the effective nuclear charge increases. Ionization energy increases from left to right. Increases from left to right. Why ionization increases from left to right? Because the reason is atomic radius decreases. Atomic radius decreases and effective nuclear charge increases. Effective nuclear charge increases. Therefore, ionization energy increases from left to right. Why? Because ionization energy is directly proportional to the effective nuclear charge and it is inversely proportional to the atomic radius. For example, this is atom, here nucleus, this is electron. If the force of attraction between nucleus and electron is more, then more energy is required to remove electrons. Okay, as the effective nuclear charge increases, ionization energy increases. From left to right, atomic radius decreases, effective nuclear charge increases. That's why ionization energy increases from left to right. Next, in a group, ionization energy decreases. Ionization energy decreases from top to bottom. From top to bottom. Why ionization energy decreases? Because from top to bottom in the periodic table, atomic radius increases, effective nuclear charge decreases. That's why ionization energy decreases from top to bottom. The reason is atomic radius increases and effective nuclear charge decreases. As effective nuclear charge decreases, ionization energy also decreases. This is the trends of ionization energy in the periodic table. But there are exception cases. Now let us discuss exception cases. I am considering second period elements. In the second period elements, what are the elements are present? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. According to general trend, ionization energy increases from left to right. Now arrange ionization energy of second period elements in increasing order of their ionization energy. This is the order, ionization energy order. This is expected order. This is expected order. But the real order is different than expected order. The real order is lithium, boron, next beryllium, next carbon, next oxygen, next nitrogen, next fluorine and next greater neon. This is the real order. In second period elements, there are two exception cases. One is the exception case in between boron and beryllium. The second exception case is in between oxygen and nitrogen. In expected order, boron has more ionization energy than beryllium, but in real order, beryllium has more ionization energy than boron. Next, here oxygen has more ionization energy than nitrogen, but in real order nitrogen has more ionization energy than oxygen. Next here, the ionization energy of noble gas element, that is neon, as greater than fluorine ionization energy. Why noble gas elements have more ionization energy? Because they have stable electronic configuration. The ionization is directly proportional to the stability. As stability increases, ionization energy increases. Noble gas elements, noble gas element have maximum ionization energy. Ionization energy. Why they have maximum ionization energy? Because they have stable electronic configuration. Because they have stable electronic configuration. Stable electronic configuration. Now let us discuss why the ionization energy of beryllium is greater than boron and why ionization energy of nitrogen is greater than oxygen. Now let us discuss exception cases. The first one, ionization energy of beryllium is greater than boron. Now you write atomic number for both elements. What is the atomic number of beryllium? 4. What is the atomic number of boron? 5. You write electronic configuration for both atoms. For beryllium, the electronic configuration is 1s2, 2s2. For boron, 1s2, 2s2, 2p1. Now tell me, between these two electronic configuration, which is more stable? This is more stable. Why it is more stable? Because it is a completely filled electronic configuration. It is completely filled. It is completely filled electronic configuration. That's why it is more stable compared to this one. Because of more stable, the amount of energy required to remove first electron from beryllium is more as compared to the amount of energy required to remove first electron from boron. Okay, that's why the ionization energy of beryllium is greater than boron. Ionization, the first ionization energy of beryllium is greater than boron. Why? Because of more stable. But after removal of one electron, from beryllium and boron, the boron attains a stable electronic configuration. Beryllium, it attains unstable electronic configuration. See here, after removal of one electron from both atoms, boron attains stable electronic configuration. Stable electronic configuration. See, after removal of one electron, the electronic configuration of boron becomes 1s2, 2s2. After removal of one electron, the electronic configuration of beryllium becomes 1s2, 2s1. Just I am writing here beryllium and boron. After removal of one electron, the electronic configuration becomes 1s2, 2s1. Here 1s2, 2s2. Now tell me, between these two electronic configuration, which is more stable? This is more stable. Why it is more stable? Because it is completely filled electronic configuration. Completely filled electronic configuration. That's why it is a more stable electronic configuration. In this case, the amount of energy required to remove second electron from beryllium is less as compared to the amount of energy required to remove second electron from boron. That's why the ionization energy, second ionization energy of boron is greater than beryllium. The second ionization energy of boron is greater than beryllium. Next, second exception case, ionization energy of nitrogen is greater than oxygen. Why? Just you write atomic number for both atoms. What is the atomic number of nitrogen? 7. Oxygen 8. Now you write electronic configuration 1s2, 2s2, 2p3. Next for oxygen 1s2, 2s2, 2p4. Now tell me, between these two electronic configuration, which is more stable, P3 or P4? P3 is more stable. Why? Because it is half-filled electronic configurations. It is half-filled electronic configuration. That's why it is more stable electronic configuration than oxygen. That's why, because of more stable, the amount of energy required to remove first electron from nitrogen is more as compared to the amount of energy required to remove first electron from oxygen. That's why ionization energy, first ionization energy of nitrogen is greater than oxygen. But after removal of electron, electronic configuration of nitrogen becomes 1s2, 2s2, 2p2. Oxygen electronic configuration becomes 1s2, 2s2, 2p3. After removal of electron, from both atoms, oxygen attains stable electronic configuration. That's why the second ionization energy is greater than nitrogen. See here, nitrogen and oxygen. After removal of electron, the electronic configuration of nitrogen is 1s2, 2s2, 2p2. Okay. The electronic configuration of oxygen becomes 1s2, 2s2, 2p3. Now tell me, between these two electronic configuration, which is more stable? This is more stable. Why? It is half-filled electronic configuration. Because of half-filled, it is more stable. Because of more stable, the amount of energy required to remove second electron from oxygen is more as compared to the amount of energy required to remove second electron from nitrogen. That's why the second ionization energy of oxygen is greater than nitrogen. These are the exception cases. The next physical property is electron affinity. What is electron affinity? The tendency of an isolated neutral gaseous atom to attract extra incoming electron is called electron affinity. For example, this is isolated neutral gaseous atom. In isolated neutral gaseous atom, the number of electrons and number of protons are same. This is extra incoming electron. The tendency of an isolated neutral gaseous atom to attract the extra incoming electron is called electron affinity. The tendency to attract extra incoming electron by an isolated neutral gaseous atom is called electron affinity. The electron affinity is measured by electron gain enthalpy. It is measured by electron gain enthalpy. What is electron gain enthalpy? Now let us discuss about electron gain enthalpy. The electron gain enthalpy is denoted by delta H Eg. What is electron gain enthalpy? The amount of energy released or absorbed when electron is added to isolated neutral gaseous atom is called electron gain enthalpy. the amount of energy released or absorbed when an electron is added to isolated neutral gaseous atom is called electron gain enthalpy. Example, this is a isolated neutral gaseous atom. When electron is added to isolated neutral gaseous atom, the neutral gaseous atom will become negative gaseous ion. It is converted into negative gaseous ion. During the addition of electron to neutral gaseous atom, energy can be released or absorbed. It depends on element. That's why the delta H Eg values are negative or it may be positive. It depends on element. If energy is released, then the delta H value is negative. If energy is absorbed, then it is indicated by positive sign. Electron gain enthalpy, maybe it is exothermic or endothermic. It depends on element. Electron gain enthalpy may be exothermic or endothermic. What is the meaning exothermic and endothermic? If energy is released during the addition of electron to neutral gaseous atom, then that process is called exothermic. If energy is absorbed when electron is added to neutral gaseous atom, then that is called endothermic. Endothermic means energy absorbed. Exothermic means energy released. For exothermic reactions or exothermic process, the delta H values are negative. For endothermic, delta H values are positive. Next, if greater the energy released when electron is added to neutral gaseous atom, if that element releases more energy, then that element have more electron affinity. Greater the energy released, then greater the electron affinity of an element. Greater the energy released, then greater the electron affinity of an element. For example, when electron is added to neutral gaseous atom, if this neutral gaseous atom it releases more energy, then we can say that this neutral gaseous atom have more electron affinity. Okay, it depends on energy released. So negative, the energy released is indicated by negative values. So negative of delta H increases, then electron affinity increases. The electron affinity of an element is depends on negative values of delta H. For many elements, delta H Eg values are negative. In the periodic table, for many elements, when electron is added to neutral gaseous atom, they release energy. That's why their delta H values are negative. But some elements like noble gases, for noble gases, when electron is added, they don't release energy, they absorb energy. For noble gases only, the delta H value is positive. Now let us discuss one example. Examples. Group 17 elements or halogens have group 17 elements. Group 17 elements are halogens. Halogens have high negative electron gain enthalpy. Negative electron gain enthalpy. Electron gain enthalpy. Group 17 or halogen elements have high negative electron gain enthalpy. High electron gain enthalpy, that means they have more electron affinity. They have more electron affinity, right? Because electron affinity depends on negative electron gain enthalpy. Why group 17 elements have more electron affinity? Because they attain stable electronic configuration just by gaining one electron. The reason is they attain stable electronic configuration. Stable electronic configuration by gaining one electron. By gaining one electron. Just by gaining one electron, the halogen elements electronic configuration becomes stable. That's why they have more negative electron gain enthalpy. Now let us take one example. Fluorine. What is the atomic number of fluorine? 9. Electronic configuration 1s2, 2s2, 2p, 5. Just add one electron to neutral gaseous atom. When electron is added to neutral gaseous atom, then the neutral gaseous atom becomes negative gaseous ion. This is the negative gaseous ion. Now the electronic configuration becomes 1s2, 2s2, 2p6. See here, compared to this electronic configuration is more stable. Just by gaining one electron, halogens or group 17 elements electronic configuration becomes stable. That's why they have more electron affinity, or they have more negative electron gain enthalpy. For halogens, the delta H Eg values are more negative. Because of more negative, they have more electron affinity. They have high electron affinity. Now let us discuss exception case. Exception. Noble gases have large positive electron gain enthalpy. Noble gases have large positive electron gain enthalpy. Positive electron gain enthalpy. Electron gain enthalpy. See here, for many elements the delta H value is negative, but only for noble gases the delta H value is positive. Why noble gas elements have large positive electron gain enthalpy? Why? Because the noble gases have stable electronic configuration. Because of stable electronic configuration, noble gas element will not accept extra incoming electrons. The reason is they have stable electronic configuration. Stable electronic configuration. For example, neon. What is the atomic number of neon? 10. Write electronic configuration 1s2, 2s2, 2p, 6. See here, the outermost shell is completely filled. That's why they don't accept incoming electron. They will not accept incoming electron. In this case, to add extra electron to noble gases, we need energy. That's why the delta H values are positive. In this case, to add electron we need more energy. That's why delta H values are positive. Delta H values are positive, that indicates electron affinity is low. That means noble gases have low electron affinity. That means noble gases have less tendency to accept incoming electron. Why? Because more stable electronic configuration. Noble gases have less tendency to accept incoming electron, okay. This is the exception case, but for many elements the delta H value is negative, but only for noble gases the delta H value is positive. Next concept is trends of electron affinity in periodic table. In a period, electron affinity or negative electron gain enthalpy increases from left to right. Electron affinity or negative electron gain enthalpy, increases from left to right. Why negative electron gain enthalpy or electron affinity increases from left to right? Because from left to right in the periodic table, atomic radius decreases, effective nuclear charge increases. That's why electron affinity or negative electron gain enthalpy increases from left to right. The reason is, from left to right in the periodic table, atomic radius decreases. And effective nuclear charge increases. That's why electron affinity or negative electron gain enthalpy increases from left to right. For example, see, it is a large atom. This is a small atom. In large atom, there is a large distance between nucleus and outermost electron. In small atom, there is a small distance between nucleus and outermost electron. In large atom, due to more distance, long distance, here there is a less attraction between outermost electron and nucleus. That's why the large atoms have less tendency to attract incoming electron. The large atoms have less tendency to attract incoming electron. But in small atom, there is a small distance between nucleus and outermost electrons. Because of small distance, there is a large effective nuclear charge. Because of more effective nuclear charge, small atoms have more tendency to attract incoming electrons. As size decreases, effective nuclear charge increases. As effective nuclear charge increases, the electron affinity increases. Next, in a group. In a group, electron affinity or negative electron gain enthalpy decreases. Electron affinity or negative electron gain enthalpy. Negative electron gain enthalpy decreases from top to bottom. Why the electron affinity or negative electron gain enthalpy decreases from top to bottom? Because from top to bottom, atomic radius increases, effective nuclear charge decreases. That's why electron affinity or negative electron gain enthalpy decreases from top to bottom. The reason is atomic radius increases. And effective nuclear charge decreases. Effective nuclear charge decreases. Just reverse here. As atomic size increases, distance increases. As distance increases, effective nuclear charge decreases. So the affinity, electron affinity decreases. This is the trends of electron affinity in periodic table. Now let us discuss some exception cases. Exceptions. Just I will take some elements: oxygen, sulfur, selenium. Next, fluorine, chlorine, bromine. Now, according to general trend, in a group, electron affinity or negative electron gain enthalpy decreases, right? According to this trend, oxygen has more negative electron gain enthalpy than sulfur. Sulfur has more negative electron gain enthalpy than selenium. Next, fluorine has more negative electron gain enthalpy than chlorine. Chlorine has more negative electron gain enthalpy than bromine. This is general order, but there is exception case between oxygen and sulfur and fluorine and chlorine. This is wrong order. The real order is sulfur has more negative electron gain enthalpy than oxygen. Chlorine has more negative electron gain enthalpy than fluorine. This is the correct order. Why? Sulfur has more negative electron gain enthalpy than oxygen, and why chlorine has more negative electron gain enthalpy than fluorine. Now let us discuss. Just I will write 4 elements: oxygen, sulfur, fluorine and chlorine. See here, what is atomic number of oxygen? 8, sulfur 16, fluorine 9, chlorine 17. Now you write electronic configuration for oxygen: 1s2, 2s2, 2p4. For sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. Next, for chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. For fluorine, 3p5. For fluorine, 1s2, 2s2, 2p5. These are the electronic configuration. In oxygen and fluorine, the outermost energy level is 2. See here, the outermost energy level is 2. The second energy level is outermost energy level. Second energy level. Second energy level. Next, in sulfur and chlorine, the outermost energy level is 3. See here, the outermost energy level is 3. Third energy level is outermost energy level. Third energy level. Third energy level is outermost energy level in sulfur and chlorine. Now let us see. Second energy level is smaller than third energy level, right? So the second energy level size is smaller than third energy level. Third energy level is larger in size as compared to second energy level. This is also second energy level, that's why it is in smaller in size. It is in larger in size. Here, due to small in size, there is a small area. Due to small area, here the electrons are arranged very close to each other. Electrons are arranged very close to each other. Very close to each other. But in case of third energy level, here electrons are arranged far away from each other. Why? Because there is a large space in third energy level. The electrons are arranged far away from each other. Now, when extra electron is added, this is extra electron. When this extra electron is added to oxygen or fluorine, this extra electron will goes to second energy level, right? It will goes to second energy level. When it goes to second energy level, this added electron experience more force of repulsion from
other electrons present in second energy level. Why? Because in second energy level, due to small area, all electrons are very close to each other. When the extra electron is added to second energy level, there is a more repulsion between electron and electrons. If same extra electron is added to sulfur and chlorine, this electron goes to third energy level and it experiences less force of repulsion from other electrons present in the third energy level. Why? Because here in the third energy level, all electrons are far away from each other. That's why the added electron or extra electron experience less force of attraction. That's why oxygen and fluorine, they have less tendency to accept incoming electron, but sulfur and chlorine have more tendency to accept incoming electron. Why? Because here there is a less force of repulsion. Here because of more repulsion, because of more force of repulsion, oxygen and fluorine have less tendency to accept incoming electrons. That's why sulfur has more negative electron gain enthalpy than oxygen. Chlorine has more negative electron gain enthalpy than fluorine. Why oxygen and fluorine elements have less negative electron gain enthalpy than sulfur and chlorine? Because when an electron is added to oxygen or fluorine, added electrons goes to second energy level, but the second energy level is in smaller in size. Due to smaller in size, the added electron suffers more force of repulsion from other electrons present in the second energy level. Therefore, oxygen and fluorine have less electron affinity or negative electron gain enthalpy. And why sulfur and chlorine have more negative electron gain enthalpy? Because when an electron is added to sulfur or chlorine, added electrons goes to third energy level. In third energy level, due to large area, the added electrons suffers less force of repulsion from other electrons present in the third energy level. Therefore, sulfur and chlorine have more electron affinity or more negative electron gain enthalpy. The next concept is successive electron gain enthalpies. When electron is added to neutral gaseous atom, the neutral gaseous atom is converted into uni-negative gaseous ion. This is uni-negative gaseous ion. During this process, they release energy. That's why delta H values are negative. Delta H values are negative. The released energy is denoted by negative sign. When electron is added to uni-negative ion, the uni-negative ion is converted into di-negative ion. During this process, the delta H value is positive. Delta H value is positive. Why the addition of electron to uni-negative ion is endothermic? Positive means endothermic, because here ion is negatively charged and the extra incoming electron also negatively charged. Due to same charge, there is a more electron repulsion between incoming electron and the negatively charged ion. That's why the negatively charged ion will not accept the incoming electron. That's why to add electron to negative uni-negative ion, we need energy. That's why delta H is positive. This is the successive electron gain enthalpy. We will continue in next class. Thank you.